Greetings and welcome to a new video about DC series motors. This is our example number 3. In this example I will discuss in great detail the efficiency of a motor. So let's move on. We have a DC series motor with this specification, 230 volts and 19 kilowatts. It has an armature resistance of 120 milliohms and also a field resistance of 60 milliohms. And this motor requires a current of 64 amps when the shaft speed is 56 radians per second. That is the given. Okay, what we want is the following. Calculate the shaft speed if the motor draws a current of 84 amps. So in a different situation. And also the efficiency for both cases. So what is the efficiency when the motor requires 64 amps? And what is the efficiency when the motor requires 84 amps. So that is also a comparison we need to make in efficiency. Alright, let's look at our solutions. And again, we begin with a model. This is our DC series model. Again, the terminal voltage, the current, which is then the terminal current, and also the field part, the armature part, and also the back EMF, which is then connected to the moving, rotating part. Alright, this is the model. And again, we know that this is a series. That means the currents are all equal to each other. So the terminal current is equal to the field current, also equal to the armature current. So we can use one of these to calculate the required values. In addition, we see from the specification we have 230 volts and also 19 kilowatt. That means the following again. The terminal voltage, the first one, is the 230 volts. And the second one is the input power to this system, which is then 19 kilowatts. And this input power is required to calculate the efficiency of this situation. Okay, let's look at the solution and start first with the shaft speed, omega sub n. In this case, we have again the familiar formula to determine the currents here and also the voltages. What we have is again using Kirchhoff voltage law, the voltage across these two nodes is the voltage across these 5 elements. We have the 2 resistors and 2 inductors and also the back EMF. But we know that the system is operating at DC. That means the reactances of these 2 inductors will be 0. So that goes away, and that will then simplify the formula in this form. So you only have the armature resistance and also the field resistance here, and also the back EMF and also the current. It depends, of course, what you prefer to use the current. I prefer most of the time to use the armature current, so that's actually what's shown here. Okay, now we can use this formula to calculate the required shaft speed. Let's move on for the first case. In this first case, we consider the situation which is given in the example, which is then 64 amperes, and then the shaft speed is already given there. So we can now work out the formula here, just substitute the given values, 230 volts for the terminal voltage, the back EMF is still unknown, we have the current, we have also the 2 resistor values for the armature and also the field part, so we can just calculate what the value of the back EMF is. And this is only valid when the shaft speed is 56 radians per second or the required current is 64 amps. Now, I have just denoted this by E sub A and then comma 64, just to mention that this is 64 amps. We have also this formula in order to go to the required shaft rotation speed. So we have this, and we can again calculate what the required value is for the second case, for the 84 amps. But before we move on, we need also know what the motor constant is. So we have now the necessary information here to go to the motor constant. So if I then substitute the values for this case with a current of 64 amps and also the rotation speed we have for the shaft, we can then determine the constants which will be also available in the second case. So that will be then, if you do the math here, you will get 3.90 Webers. That's actually our motor constant. So we can then use that for the next situation. Now let's look also to the second case for a terminal current of 84 amps. Now we have now again the same expression, but then in this case we have for the terminal current or the armature current, which you prefer, is 84 substitute again the given values, you will have for this situation the back EMF voltage of 214.9 volts. Alright, now we can move on again using this formula, and specifically then for 84 amps, again specified here in the subscript. And I can use now also the motor constant that won't change, so that's still 3.9. If I now substitute the values for the back EMF and also the motor constant, I will get 55.1 radians per second. And that's the question actually for A. This is the shaft speed for 84 amps. So by increasing the current, you will decrease your shaft speed. It's actually shown here. Okay, the second one is the efficiency. Efficiency is defined by the output power divided by the input power, so the ratio of that. And we know that the input power from specification is 19 kilowatts or 19,000 watts. And we know that the output power is equal to the developed power here. That is then the product of the back EMF and also the armature current. Or it is a back EMF and also the terminal current, which you prefer because it's a series connection. So for the first case, when the terminal current is 64 amps, we have again this formula. Just use the values for the right current value, which is then the back EMF here and also the right current for the armature or the terminal. Then we have this power, so it is then approximately 13,984 watts. Now we can calculate the efficiency. Efficiency is then given again by the P out over P in. We know the P out or the PD, it's exactly the same. And we have the P in, and we can now calculate what the value is in scalar form, which is then 0.736 or 73.6%. Now in a similar form, we can do that for the next case where the current is 84 amps. Again, using the same formula for the developed power, which is equal to the output power. Again, using the correct back EMF and also the correct current value for this case, the product of this will give you 18,052 watts, approximately this. Now, again, calculating that efficiency for this case, you will get a value of 0.950. That will be then 95%. So you can see by increasing your terminal current, you increase your efficiency. And what you also have is by increasing your terminal current, you will decrease your shaft speed. So by increasing actually your shaft speed, you will decrease your efficiency. So that's actually that's the relationship between the shaft speed and also the efficiency. So by making your shaft speed higher, you will have also lower efficiency. And that is the conclusion for this example. I hope this clarifies the situation in great detail. Also again, looking to the efficiency part and which parameters of this series DC motor will have an effect on the efficiency. If you have any questions, please let me know. I will try to answer them as soon as possible. See you next time in another interesting video. See you next time and take care.